In modern AI, a system rarely returns an immediate answer to a difficult prompt. It pauses, searches, evaluates, and corrects its logic before speaking. This is inference time compute. Instead of relying on a single prediction, developers wrap models in structural scaffolds that allow the system to repeatedly prompt, critique, and repair its own work. This method has led to performance gains in complex search tasks, from Olympiad geometry to mathematical reasoning. These breakthroughs have fueled the assumption that scaling this internal repetition will eventually lead to a system that qualitatively improves its own intelligence. The problem is that this conflates a model using its current resources for a longer duration with a model acquiring a stronger capability regime. To find the actual boundary of self-improvement, we have to look to classical computability and complexity theory. The math indicates that finite internal revision inside a frozen AI model does not result in qualitative capability ascent. To prove this, we can map agentic workflows to a two-axis mathematical framework. One axis represents structural verification ascent, or the depth of the inference scaffold. The other represents training-driven mechanization. Distinguishing these two paths is the only way to separate temporary performance gains from a permanent increase in a system's relative level. The framework starts with a base layer, a zero-shot model performing unassisted prediction. This baseline capability maps to the complexity class P. It represents tasks solvable by a single deterministic procedure with no auxiliary help. If we augment this model with a protocol that checks its work, we move into a different regime. This is NP, or polynomial time certificate verification. The model may struggle to find a solution from scratch, but can confirm one is correct in a single pass. This is the first rung of the polynomial hierarchy, a series of levels that categorize how adding stages of checking and repair expands a system's reach. Adding a verifier allows the model to solve more problems in practice, but the underlying complexity limits of that base model are still in place. Advanced AI scaffolds often go beyond a single check, employing a multi-stage loop of proposal, critique, and repair. This bounded verification game uses alternating quantifiers. The first stage, exists y1, proposes an initial candidate. The critique, for all y2, tests that candidate against failure modes. Finally, exists y3 proposes a repair based on that critique. Every added stage of this bounded game moves the system one step higher along the vertical axis of the hierarchy. Deeper scaffolds allow a system to reach more solutions, but they are still procedures composed of the model's existing logic. They expand the volume of what the model can find without changing its core intelligence. This raises a question. If scaffold depth increases reach, can we simply stack these loops until the system achieves a higher degree of capability? The answer lies in the study of computational limits, pioneered by Alan Turing. We can define the total capability class available to a system as its computational layer, or C of A. The formal roadblock here is a property called local closure. If the rule used to update the model is itself a function the model can already perform, then every resulting state is part of the original capability layer. You cannot reach a qualitatively stronger regime using only the logic you already possess. This remains true even if the process is modeled as stabilized revision, where the system's corrections converge to a final limit. The relativized limit lemma shows that while the limit of such a process equates to a higher level, the turning jump, the system cannot reach that limit through finite iteration alone. To bridge the gap, the system needs guidance that does not currently exist within its own procedures. That guidance comes from external resources, human supervision, environmental feedback, or search traces the model cannot generate on its own. Capability internalization is the process of taking that external guidance and baking it into the architecture of a successor system. This is the role of training. Once a task that was previously impossible is internalized, the model no longer needs external aid to solve it. This shift moves the system along the horizontal x-axis of our grid. By internalizing guidance, the system establishes a new computational layer, C of B. The ceiling of the old regime becomes the floor of the new one. This transition represents the formal Turing jump, where the successor system is demonstrably more capable than the system that preceded it. Capability ascent requires this transition. You must step out of the inference loop and mechanize knowledge into a brand new model. Using this two-axis framework, we map the geometry of AI progress. A vertical move increases reach via verification stages, remaining in the original capability layer. A horizontal move transitions to a stronger degree, mechanizing scaffolds into a new baseline. Scaling is not a smooth curve of self-improvement. It is a sequence of these discrete steps. Repeated internal revision on the vertical axis can never achieve the jump in capability provided by training on the horizontal axis. This distinction explains why even the most complex inference loops eventually encounter a performance plateau. These mathematical proofs provide a standard for evaluating future AI systems. Building smarter agentic loops and deeper scaffolds is necessary to reach the full potential of current models. But claims of open-ended recursive self-improvement should be weighed against the reality of computational layers. Progress depends on identifying whether a breakthrough involves deeper verification structure or the mechanization of previously external guidance. The boundary of inference is defined by the logic of the system. To surpass it, we must rely on the structural discipline of training-driven mechanization.